Okay, so section 4, we're going to look at solving equations. And, again, what I want to do to begin with is make sure that we have all of the terminology down. Okay, so we're going to start with a definition. So, a linear equation in one variable. Sort of a mouthful, but all we're doing is we're saying that we have an equation that has just one variable in it. So back in the last example, when we had like y equals 2x plus 3, I had two variables, x and y. When we talk about a linear equation in one variable, we still have an equation, so there's an equals in there, but we only have a single variable. Okay, usually that's going to be x. Doesn't have to be. All right. And in order to be linear, we have to be able to write it in that mx plus b form. So it's going to be an equation that could look like this, right? Mx plus b. However, it doesn't have to be quite that neat. One way to think about this is that everything that has an x in it is either a constant or just an x. There's no like x squareds or square roots or anything like that. Okay. Typically, we can't really have any fractions with like an x in the denominator, although that's not strictly speaking true, but I think for our purposes, we'll be safe with that. So we just want like x's and numbers, and that's it. Okay, so here we have two examples of things that are not a linear equation in one variable. In the first one, I can see because the x has a squared in it, it's not linear. Okay. In the second one, I have two variables. I see a y, I see an x, so this is not linear. Or sorry, this is not one variable. This is two. Okay, so now I want to maybe come back a little bit and look at the difference between what I have here and what we have up here. Because mx plus b, I see three letters. Why is that one variable? Okay, when we talk about writing things in the form y equals mx plus b, here what we're doing is we're using m and we're using b as placeholders for a constant number. Okay, so they're not a value that can vary. They're a constant, and in practice, they're going to be like a concrete number that we can see. Okay, so these are constants, not, or you could think of it as like an unknown constant, not a variable. Okay, so we can be a little bit tricky here, but in practice, when we actually see our equations, it won't be so tricky because those constants won't be unknown. We'll see a value for them. Okay, so here we have an example, 4x plus 10, and that is in the form of mx plus b. One of the things we have to be careful about is that what I have here on the left is an expression. Okay, what we have on the right is an equation. And we don't solve expressions. That doesn't really have any meaning. We can evaluate an expression by plugging in a value for x and computing what the number is that we have resulted. But solving an equation is different. Solving an equation is finding the x value that makes it a true statement. Okay. So we evaluate expressions, we solve equations. All right, so let's look at some examples where we see the difference between the two. Well, all right. let's talk about equivalent expressions, and then we'll see the difference between evaluating and solving. So equivalent expressions, when we have two expressions, and no matter what I plug in for x, those two expressions are going to be equal, then those expressions are equivalent. Okay, so when I look at 4 times parentheses 2x plus 3, and I look at 8x plus 12, it's not like 1 or 2 x values that will make this a true equation. It's every x value. Okay, every value for x will make this equation true. Okay, so these expressions are equivalent. Okay, so when we solve an equation, we're looking for what x values make them true, and usually it's going to be 1, or maybe 2 or 3. Okay, when it's all of them, then what we had to begin with was equivalent expressions. Okay, so let's look at equivalent equations now. So that was equivalent expressions. Equivalent equations are equations that have the same solutions. Okay, so the same ordered pairs make that equation true and make that equation false, right, as the other equation, right? So let's look at some examples. Okay, evaluate 4x plus 10 for x equals 5. Okay, so what I'm going to do is evaluate this expression by plugging in this x value. So I replace the x value in parentheses, or the x with its value in parentheses. Okay, so I have 4 times 5 plus 10, which is 20 plus 10, which is 30. Okay, so I have evaluated this expression. Now, let's have another question. Is x equals 5 a solution to 4x plus 10 equals 22? I don't have to do any work here because I already know that when 4x plus 10, when x is equal to 5, 4x plus 10 evaluates to 30. Okay, so I know that when x equals 5, I would have 30 equals 22, which is false. So x equals 5 is not a solution. Okay, so what we're doing here is we're making a connection, right? Here I evaluated an expression. Here I was solving an equation, and we, we sort of tied the same work together in order to do those. Okay, let's look at another one. Consider the following equation. 6 minus 2 equals 4. This equation is true because if I add 2 to both sides, on the right, I would have 6 minus 2 plus 2, which is the same as 6. And if I take 4 and add 2, I get 6. Okay. So by adding 2 to both sides, I get another expression, or sorry, another equation. Okay. And this one is also true. Okay. So what we're doing here is just kind of going back to stuff that you know, that you've learned before, and just sort of, talking about what it means, right? So we have this addition property of equality. If A and B are expressions and C is any number, then A equals B is equivalent to A plus C equals B plus C. Okay. that means that they have the same solution. So by adding the same number to both sides of an equation, I get an equivalent equation. Okay? That's why we can do the algebra steps that we do, right? We don't just like make those rules up out of nowhere. What happens is that if my two expressions were equal, so I have, a true equation, when I add the same number to both expressions, I have a different expression now. I have a different number. But if the first two were equal, then the second two have to be equal. Okay, so my equations are equivalent. Okay, I haven't changed the solutions by adding stuff to both sides. So when we take an expression and just add a number to it, we've changed the expression. When we take an equation and we add a number to both sides, we keep the same solutions, right? So it's still an equivalent equation. All right. Let's look at another example. The difference between the number of dependents and 2 is 10. Okay. So what I want to do to begin with is give a variable to this unknown thing. Okay. So what I'm going to do is I'm going to say the number of dependents I'm going to represent with a variable x. Okay. The word difference tells me that there's subtraction. Okay. So it's the difference between the number of dependents and 2. So I want subtraction of x and the number 2. Okay. The word is means equals. Okay. And then I just have the number 10 hanging out, so we'll write our 10. So the equation that I want to begin with is x minus 2 equals 10. Okay. This has the same solution as the equation where I add 2 to both sides. So if I take x minus 2 and add 2 to the right, and also add 2 to my left, add 2 to the left and add 2 to the right, then my new equation, minus 2 plus 2 is 0. So I have x, and 10 plus 2 is 12. So x minus 2 equals 10 has the same solution as x equals 12. And there I can just see I'm done, right? That's my x value. Okay. To verify that x equals 12 is a solution to x minus 2 equals 10, okay, what we can do is say, well, if I could plug in, I could say plug in x equals 12. So 12 minus 2 equals 10. And 12 minus 2 is 10. Right? So I've double checked it. Yes, 10 equals 10 is true. So since x equals 12 makes the equation true, x equals 12 is a solution to x minus 2 equals 10. Okay, the goal here is to make sure that we have our terminology straight and we sort of understand the steps behind what we're doing. Okay, I don't think that x minus 2 equals 12 is a difficult equation for any of us. That's not the point. What we want to do is maybe think more deeply about this process that we have of solving equations. And we don't want to think of, when we start a math problem, just automatically doing some algebra things because we're sort of programmed to do that. We want to think about it a little bit. And the reason that's going to be helpful is when we start doing modeling, when I look at a real life situation and I want to model it with a math equation, we have to kind of think about, where to start. We don't have an equation to start with to just, do our stuff. We want to make sure that we're, thinking carefully about the whole process so we know how to start. And then when we get a number answer, we know what it means. Right? That's the real goal. We want to make sure that we can connect some meaning to our numbers at the end. Okay, so that's why we're going through this in such detail. All right, let's look at another way to solve an equation. Use the table feature on the calculator to find solution to the equation that we wrote. Okay, so what I'm going to do is go back and remember my equation. Was, x minus 2 equals 10. In order to make a solution here, to put it on my calculator, I need two variables. Okay, so I want my calculator to be able to do some work for me, but we have to be a little bit careful about that. What we're going to do when I look at this original thing that I wrote, right? So we're going to start with x minus 2 equals 10. We want to find out when our two expressions are equal to one another. So what I'm going to do on my calculator is I'm going to say, all right, let y1 equal the first expression, x minus 2, and let y2 equal the second expression, which is 10. Okay, so I'm going to do that on my calculator. So I go to the y equals, and get rid of the stuff that we had before. So I'm going to put x minus 2 as my first expression, right, and the y1, and 10 as the second one. Okay. What are we looking for here? What I want is I want these two things to be equal, right? So if I look at my table of values, what I really want is I want my y1 and my y2 to be the same number. That's when the two sides are going to be equal. So I get a solution when these two expressions are equal. So what I can do is I can just scroll down and look for where is y1 equal to y2. And then I say, oh, I found it. Here where y1 is 10 and y2 is 10, that's where the expressions are equal. And that happens when x is equal to 12. Okay. So what we're looking for in the table, we're looking for the y1 and y2 column to match. Okay. Right. And if I go back up, if I just fill in the first few lines of this, right, they don't initially, right? I have -2, 10, -1, 10, 0, 10, and so on. But when I get down to 12, that's when they're going to match. Okay. So when these match, okay, the x value is our solution. Okay, I want to do this same thing a different way. Let's do this using a graph instead on my calculator. So I'm gonna do the same thing, right? I'm gonna start with the equation x minus 2 equals 10, and I'm gonna let y1 equal the first expression x minus 2, and I'm gonna let y2 equal my second expression 10. And what I can do is I can hit graph. Now, just hitting graph is not always the most helpful. What I want to do is make sure that things fit properly in my graph. Okay. So one thing that we can do is we can hit zoom and hit like we can mess with zoom windows. Okay, the standard zoom is what we were just on. But if I hit window, then I can adjust where my graph starts and stops. Okay, And if I wanted to match my table, right, we started at an x value of 0. Okay. Right, and I can hit graph. And I can see, oh, I need to go over a little bit more. Maybe I need a bigger x value. So let's have the x max go out a little bit more, maybe out to 15. Also, it was a little scrunched on the top, so let's have our y value go up a little higher. Maybe that'll go out to 15 instead of 10. Okay. All right, now remember the graph is going to be all of the solutions, the equation, the ordered pairs, right? And what we want is we want y1 and y2 to be equal to each other. So we want those to give me the same y value. So what we're doing is we're looking for a point on the graph where we have the same y value. Okay. And I'm looking for one x value that makes them both the same y value. So what I'm really looking for is where the two graphs intersect. Okay. All right. So if we made our x max like maybe 15 or so, then we can look on there. And we're looking for the intersection of the two graphs. Okay. And so on my calculator, one way to do that is I can hit trace and I can kind of move along. The downside here is that when I'm tracing along, I'm not really sure where exactly that intersection point is. Okay. So if I wanted to be a little bit more precise about it, right, because this is saying an x value of 11.96, and it can hit up and down to jump between the two graphs, right? And what I'm trying to do is find out where they're equal, but I don't want to spend all day sort of jumping between graphs and moving small amounts left and right. So one of the things we can do is if I hit second and hit calculate, right down here it says find the intersect point. I say that's what I want. Yeah. So the first curve, I select one of them, hit enter. The second curve, yep, that's the other one. Hit enter. And it wants you to give it a guess. So you just give it a point nearby, but really you don't even have to be that careful. And it says here's the intersection. X is exactly 12. Okay, so you don't have to mess around with a bunch of zooming if you use that intersect feature. Okay, so what we did is we hit second and calculate. And we went to that intersect button. Okay, to find the intersection. Okay, let's look at another example. Okay, here's our example. The sum of $9.50 and the deductible is $17.25. Okay, so write an equation and solve it using the properties of equality. So sum of means adding. So I have this first thing. And the deductible, I don't know what the deductible is, so I'm going to call that X. Okay. Is means equals. And then I have 1725. Okay. Why would this solution not appear in the table as we have it set up? If I were to type this in and follow the same steps that I did before, right, if I put this into y1, and this into y2, okay, the table that I left off with only went up, you know, it doesn't go up high enough, right? I'm not getting up to 17.25. Okay. So I might have to adjust my table. Well, let's take a look. Let's actually do this. We'll go through it. 9.5 plus x. And here's 1725. And let's look at the table. Okay. And I, just like before, I need to scroll down, right? I can see my y values are getting bigger, getting closer and closer to the y2. Closer. And then, oh, wait, we went over. So I can see at 7, y1 is smaller than y2. At 8, y1 is bigger than y2 and getting bigger. But I don't have y1 equal to y2 anywhere in my table. And if I keep scrolling, I'm not going to find it. And so I would look at this and say, I feel like we have a problem here. And the problem is that my x values in my table are by default whole numbers. And if my solution is not a whole number, then it's not going to show up on the table. Okay. So the solution is a whole number. The solution is not a whole number, but the table is only giving me whole number values for x. Okay, those y values weren't whole numbers. That's okay, but it was taking whole number steps for x. Okay, so in that case, I think that instead of using a table, it would be more, it'd be easier to look at my graph. Okay, and maybe I have to zoom out a little bit. Just hit zoom out. That's fine. To find where my lines intersect, and I can say, oh, okay, now I can see the intersection point. And I do the same steps as before. I hit calculate the intersect, right? First curve, second curve, my guess. And it gives me my intersection point exactly. And remember, we said that it was between 7 and 8. And here it says, oh yeah, 7.75 is the intersection. That's where these two hit. And so that's going to be the solution to this. Okay. So if your answer doesn't show up on the table, it's probably easiest just to use the graph. Now, you could mess around with the table and try to get that answer, but typically that's going to be a bad way to go because, you know, if you don't know what the answer is, then you don't really know how to set up the table to give you the right steps. Okay, so in this case, just use the graph. Okay, now you might be looking at this and saying, why not just subtract 9.5 on both sides? Wouldn't that be a lot easier? Yeah, it would. What we're going to do, though, is we're going to be looking at things that get a little bit more complicated later. And we just want to have ways of solving more complicated things that are, you know, just as easily. Okay. But yeah, you could have just subtracted. And if I take 17.25 and I subtract 9.5, then we'll get that 7.75 that we saw. Okay, let's look at another one. Consider the following. 6 halves equals 3. Is this equation true or false? I think that this equation is true. Okay, if we multiply both sides by 2, on the left I would have 6 halves times 2. On the right we would have 3 times 2. And dividing by 2 and then multiplying by 2 is taking us in a circle. We get back to 6. 3 times 2 is 6. Okay. So my resulting equation by multiplying by 2 is 6 equals 6. This is true. Okay. This is an example of the multiplication property of equality, right? A second ago, we talked about the addition property. We could add the same number to both sides, and that number is allowed to be negative also. We can do the same thing here, except with a different operation. We can multiply both sides of an equation by the same number and get an equivalent equation, which means we have the same solutions. Okay, and our thing that we multiply by could be a fraction, right? It could be like 1/2. So in a sense, we sort of get division for free, right? Because that's the same as multiplying just by a different number. Okay, let's look at an example. Your bill is 4/5 of the original cost. If your bill was $12, what was the original cost? So let's start by putting in some variables. Your bill, I can give that a variable name. Call that x. Your bill is, so equals 4/5. And then of the original cost, so what I'm going to do is I'm going to say, all right, the original cost, I'm going to call another variable. I'll just call it y. Okay. Then the next sentence says, if your bill was $12, that's saying that my bill, which is x, is equal to 12. And what is the original cost? So find y. Okay. So then I say, all right, well, I'm going to replace the x with a 12. And I say, okay, now I want to find y. Okay. Now, the way that I have this scaffolded, we end up solving for x. And the way that I wrote down my problem, I'm not solving for x, I'm solving for y. And that's okay. What happened was we started with a word problem, and I decided to start setting it up. Okay, and I might set it up one way, and somebody else might have set it up a different way, right? Somebody else may have said, okay, maybe I'm going to pick B for bill and C for cost. Somebody else might have read through this whole problem and said, oh, I want to find the cost, I'll call that x. Okay, maybe my bill was y, or maybe they never even bothered with the bill because they read ahead and said, oh, your bill is $12, so I don't even need to write that as a variable. Okay, so there's oftentimes more than one way of setting things up, and that's fine. When you set something up, you can just stay consistent with what you set up. Okay, so I'm going to have a starting equation of 12 equals 4/5 times y. And that has the same solution. If I wanted to get the 4/5 to go away, what I could do is multiply by its reciprocal. I can multiply by 5/4. Okay, so this has the same solution as 12 times 4/5 equals 4/5. Oops. I don't want to multiply by 4/5. That's not going to get me anywhere helpful. If I want 4/5 to go away, I'm going to multiply by its reciprocal. I'm going to multiply by 5/4. Okay. So to multiply 12 by 5/4, I recommend use a calculator. If you're doing it mentally, the division works out nicely. So I would do the division first, right? 12 divided by 4 gives me 3 times 5. 3 times 5 is 15. Okay. 4/5 times 5, 5/4 times 4/5, they're reciprocals of one another, so I just get 1. So we just get 1y or y. Okay. So I have solved for y instead of x because I labeled my variables differently. So let's verify that y equals 15 is a solution to 12 equals 4/5 y. Okay, so what I'm going to do is I'm going to plug in. I'm going to say, okay, 12 equals 4/5 times 15. And I'm going to get out my calculator to do mental math on this one too. But I'm going to take 4/5 times 15 and see that it's 12. So since y equals 15 makes the equation true, y equals 15 is a solution to 12 equals 4/5 times y. Okay, now in the next step, it's going to be confusing because I wrote things as y. So what I'm going to do is I'm going to change things around and say I should have picked a little bit more cleverly so that I had an equation with x's from the beginning. So the equation that I'm going to solve here, I'm going to say let's solve 12 equals 4/5 x instead. That way I don't have y equal y stuff where the y's mean different things. That's too confusing. So I'm going to do the same thing we did before. Let's let these y1 and y2 equal the two different expressions that I have that are supposed to be the same. So let's let y1 equal 12 and let y2 equal 4/5 x. And this is doubly handy to have changed my variable because my calculator, when I hit the y equals, my variable, that I can type in is always just going to be an x. Oops. So we're going to make the y1 12, and we're going to make the y2 4 divided by 5 times x. Okay. And we can use the table feature again. And I'm looking for where these two are equal. So I'll just scroll down, and I see, ooh, I see 12, 12. They're equal when my x value is 15. Okay, so we're looking for where y1 and y2 match. Okay. And again, the first few rows here, 12, 0, 12.8, 12, 1.6. But when I go down to x equals 15, then they're both 12s, and I have a solution. Okay, likewise on the graph, we do the same thing. I can say, all right, I want my y1 to be 12, my y2 to be 4/5 x. We've already typed that in, so we can, at this point, just hit the graph button. Now, mine is still zoomed out from the previous problem. Okay, under my standard zoom window, I won't see the intersection point. Okay, so I might have to zoom out, right? Hit zoom and just zoom out, and that's fine. Okay, and then I can see here's my two lines. I can see my intersection point. And so we hit calculate the intersection point. First curve, second curve, give it a guess, and it says, okay, the x value is 15. They both have a y value of 12. Just like in the table, the 12 is not something that we need to write down. It's the x value of 15 that we care about. Okay. So what are we looking for on the graph? We're looking for where the lines intersect. So again, if I hit second, calculate, intersect, okay, the x value of the intersection is the solution. Okay. All right, let's look at another one. The product of -5 and a number is -1.5. So again, I'm going to translate this into a math equation. Okay, so product of means multiply. So I'm going to multiply two things. Okay, so I have the product of -5. I have a number. Since I don't know it, I'm going to call it x. Is means equals. I'm running out of colors here. And then is -1.5. Okay, let's solve this using the properties of equality. Well, if I want to solve this using properties of equality, multiply both sides by something, what I want to do is multiply by 1 over -5. Okay, so if I have -5x equals -1.5, what I would do is multiply both sides by 1 over -5. Okay, that's the reciprocal of -5, so when I multiply, they would cancel, and I would just get my x. Okay. On the other side of the equation, I have -1.5 times 1 divided by -5. And I get 0.3. Okay, this wouldn't show up in the table because, again, it's not a whole number value. Okay, so if I had set this up and tried using a table, and I would say, oh, I can see that I'm not getting the two to be equal, then I would just switch over to a graph, and it's already entered in, and I can use a graph to solve it. Okay, let's look at another example. Use the graph of y equals -1/2 x. I think my half is cut off a little bit here. Let's see if we can fix it. Okay, the graph of y equals -1/2 x plus 1 to solve the following equations. Okay, so here I have the equation -1/2 x plus 1 equals 3. So I want to find an x value so that this expression on the left is equal to the expression on the right. Okay, so if I were to say, okay, y equals this, that's the graph I have given. Y equals 3 is a horizontal line. Okay, and I can see that they intersect at this point here. That's an x value of -4. So let's check our solution, right? I'm going to plug in -4 for x. So I have -1/2 times -4 plus 1 equals 3. negative 1/2 times negative 4 is a positive 2. 2 plus 1 is 3. Okay, so it checked out. All right, what about this one? I can graph y equals negative 1. I already have this graph. Okay, y equals negative 1 is this horizontal line. And I can see, all right, they intersect right here, and that's going to be when x is 4. So that's my solution. And we can check it. Negative 1/2 times 4 plus 1 equals negative 1. Negative 1/2 times 4 is negative 2. Negative 2 plus 1 is negative 1. Okay, so these are equivalent equations, and negative 1 equals 1 is true. Okay. Use the table y equals 5x minus 3 shown below to solve the following equations. So we don't have to put this on our calculator. We're given the table. Okay. What we're going to do is solve these. So if I said, okay, I want to look for where are these two the same. Okay, this y value is 5x minus 3. So what I'm doing is I'm just looking for where is that y value equal to 12. I can say, oh, here it is, and that happens when x is 3. So x equals 3. So check your solution. 5 times 3 minus 3 equals 12. So 15 minus 3 equals 12. So 12 equals 12. That's true. Okay. The next one. Where is 5x minus 3 equal to negative 13? What I want to do is I want to say, all right, this is my y value. I want to find out when is y equal to negative 13. Here it is. And that happens when x is equal to negative 2. Okay. So let's check it. So I'm going to plug my x value in. 5 times negative 2 minus 3 equals negative 13. 5 times negative 2 is negative 10. Negative 10 minus 3 is negative 13. Okay, negative 13 equals negative 13 is true. Okay. Okay, that was using tables and graphs to solve equations in one variable. Now let's look at solving equations. Let's look at some other equations. So here, what we're going to have is maybe just some more pieces. Okay. And let's just jump right into an example. Given v of t equals 10,000 minus 50t, where t is in years since 1990 and v is the value, when will the value reach 8,000? Okay, so what we're doing is I'm saying, all right, if this is my value, I want to find when it is 8,000. So 8,000 is equal to my expression for the value. Okay. So what we can do, let's look at two different ways to solve it. So method one, we're just going to use equivalent equations. So I'm going to start with 8,000 equals 10,000 minus 50t. And I want to just use my equivalent equations to find out what t is. So I have stuff added and multiplied by t. I want to get rid of it all. So I'm going to add a negative 10,000, or you could think of it as subtracting 10,000 to both sides. Okay, so 8,000 minus 10,000 is negative 2,000. And 10,000 minus 10,000 is 0, so that's gone. So I just have my negative 50t. And now what I'm going to do is multiply to get rid of the negative 50. So I can multiply by 1 over negative 50, which is the same as dividing by negative 50. Okay. And you can do mental math, but there's no extra credit for doing things mentally. So, feel free to be careful. Make sure you don't misplace a decimal. So negative 2,000 divided by negative 50 will give me 40. And negative 50 divided by negative 50 gives me 1, so I just have 1t or t. Okay, and I can check my solution, right? 8,000 equals 10,000 minus 50 times 40. And if we're going to use our calculators to check things, let's just check that whole right-hand side. 10,000 minus 50 times 40 gives me 8,000. Okay. The other method that we can use to solve this is the graph. I can say, all right, y1 is going to equal 8,000. y2 is going to equal 10,000 minus 50t. Okay, and I want to find where they intersect. So we said y1 is 8,000. y2 is 10,000. Oop, that's too many zeros. 10,000 minus 50t. I can't do t, so I'm going to use x, but that's okay. Same idea. When I hit graph, I'm not going to see the intersection. So I'm just going to zoom out. And maybe I have to do it more than once. I'll just keep zooming out until I see both lines. All right, both lines show up. One of them is really close to the axis. It's really hard to see, but that's okay. My calculator will pick it up. If I used my window, I could make this look much nicer and see them. But I'm just going to find that intersection point. First curve, y1 equals 8,000. Yep. Second curve, y2 equals 10,000 minus 50x. Yep. Guess. And it says, okay, x is 40. Okay. So my calculator told me x equals 40. I want to be careful, though, because my variable is actually supposed to be t. So we're going to use t equals 40. Okay, and we check it the same way, so I'm not going to check it again. Okay, next example. The price of product A was $20 in 2005 and has been increasing at a constant rate of $5 per year. The price of product B was $50 in 2005 and has been decreasing at a constant rate of $1 per year. When will the price of the products be the same? So this problem, we've already gone ahead a little bit and done what I think is the harder work of writing down the equation that we need to solve. Okay, so what we can do is we can say for product A, okay, well, maybe even taking a step back, I'm going to make my variable the number of years since 2005. So then the price of product A is $20 plus $5 for every year since 2005. Product B, it started at $50 and it's going to decrease. So I'm going to subtract $1 for every year since 2005. And what we want to do is find out when is the price going to be the same. So if I have an expression for price, then I just want to solve when of those two expressions equal. Okay, and that's how we get the equation that we have here. All right. So I'm going to, again, you can do this the two different ways. I'm going to show you both. So say method A and B, or method 1 and 2. Okay, so method 1, let's solve this using algebra, right? Equivalent equations. So I'm going to start with 20 plus 5x equals 50 minus 1x. And what I want to do is get x by itself. Well, x is on two sides here, so I'm going to add 1x to both sides to gather all of my x's together. Okay, so 5x plus 1x will give me 6x. Negative 1x plus 1x gives me 0. Okay, and now this looks more familiar. I'm going to subtract 20 on both sides so that we have 6x equals 30. And then finally, we divide both sides by 6. Okay, so we get x equals 5. Method 2, I'm going to say, all right, y1 is 20 plus 5x. y2 is 50 minus x. And I'm going to create a graph. So you can write 50 minus x. I should clear that one out first. You can write 50 minus x or 50 minus 1x. Okay, it's the same. When I hit graph now, my graphs are going to be real tight up on each other. That's fine. I could do the intersection point here. As long as you see them, that's fine. If you ever want to fix your zoom window, you can just hit zoom standard. Right, and bring things back to normal. And then I say, oh, wait, I can't see my graph, so I still have to zoom out at least once. Say, oh no, I'm still a little bit off. I'll zoom out a second time. So maybe fixing my zoom window was a bad idea anyway. Okay, so we hit second, calculate, intersect, first curve, second curve, guess, and it tells me x equals 5 is the intersection. Okay. To check my answer, what I'm going to do is go back to my original equation and plug in x equals 5. So 20 plus 5 times 5 is equal to 50 minus 1 times 5. So 20 plus 25 is equal to 50 minus 5. 1 times 5 is 5. 20 plus 25 is 45. 50 minus 5 is 45, and this is true. So we're good to go. Okay, I'm not going to do two solutions for the rest of these. I'm just going to solve one, and maybe I'll just go back and forth. Solve the following. 4 times the quantity x minus 2 plus 2x equals 10. So in the earlier problems, we started by getting rid of stuff on one side of the equation, typically. Sometimes we might want to not start off doing that. We might want to just pick one side of the equation and simplify it like an expression. Okay. So I'm going to distribute the 4. I have 4x minus 8 plus 2x equals 10. And I'm going to gather my like terms, right? I'm going to add 4x and 2x to get 6x. Right? And now I can start getting rid of stuff. that's around the x. I'm going to start with getting rid of the 8, or the negative 8 by adding 8. So we have 6x equals 18. And then finally, to get rid of the 6 multiplied by x, we can divide both sides by 6. So x equals 3. Okay, so then we check. So I have 4 times 3 minus 2 plus 2 times 3 equals 10. I replaced all my x's with a 3. That's my solution, right? Okay, so that's 4 times 3 minus 2 is 1. 4 times 1 is 4. 2 times 3 is 6. And 4 plus 6 is 10. Okay, so it checks out. All right. Here's another example. Like fractions, using your graphing on your calculator would be an easy way to solve this. I'm going to show you how to solve this getting common denominators, because I think that it's good to have a refresher on fractions and in particular common denominators. Okay, so let's start with 2/3 x plus 1/6 equals 1/4. And I'm only going to focus on one side of the equation, right? So on this side, I want to get common denominators. Okay, so I want to find the least common multiple of 3 and 6, which is 6. And when we say least common multiple, remember what we're doing is I'm thinking about what are all the multiples of 3, right? 3, 6, 9, 12. What are all the multiples of 6? 6, 12, 18. And what I want to do is find out which one matches both lists. And I want the smallest one that matches both lists, because I want to keep my numbers as small as possible. Okay, so my least common multiple is going to be 6, and the 1/6 is already set up for that. What I want to do is make this 2/3 have the same denominator. And in order to go from 3 to 6, I have to multiply by 2. But I can't just multiply a denominator by 2. That would give me an expression that's different. What I want to do is make sure that I'm not changing the value of my expression. So I'm going to multiply by a fancy form of 1, because multiplying by 1 doesn't change anything. Okay, so what I'm going to do here is I'm going to multiply by 2 over 2, because this is really just 1. Okay. When you multiply fractions, multiply straight across. When you add or subtract fractions, they have to have the same denominator. Okay, and then you just add and subtract the numerators and keep that denominator. Okay, so here, when I multiply, 2 times 2 gives me 4. 2 times 3 gives me 6. Okay, now I can add the fractions on the left. Okay, it might be easier, instead of thinking of this as 4/6 times x, it'd be easier if I think of the x as being 4x over 6th plus 1 over 6th. And now when I add them together, I'll get 4x plus 1 over 6th. Okay. Now I need to do this process again, because now I still have two fractions with different denominators. Okay. So one way to do this is to find, the common denominator again. Okay. Another way to do this is with a method that you probably remember from the past called cross multiplying, and that might be a little bit easier. So what I want to do when I cross multiply, a way to think about it is, in order to get rid of the denominator of 6, I have to multiply both sides by 6. Okay, so that these guys cancel. And in order to get rid of the 4, I multiply both sides by 4. And 1/4 times 4, these guys will cancel. Okay. So on the left, I have 4 times 4x plus 1. And on the right, I just have 1 times 6, or just 6. Okay. And now we can treat it like an earlier problem. Distribute the 4. Okay. Subtract 4 from both sides. And then divide both sides by 16. Now, if we're writing this as fractions, 2 over 16 is 1/8, right? Or if you wrote 0.125, that would work fine too. Okay, let's look at using your calculator to do this same thing. And I don't mean by like using a graph. We can get our calculator to actually compute common denominators. So if I hit math, I can see this convert to fraction. Okay, so if I want to get a common denominator, all right, 2 divided by 3, if I hit convert to fraction, it'll make it into the fraction 2/3, right? Depending on your calculator, you should also be able to enter fractions. So if I go to, I think here. Yeah, so let me take you through those steps again. If you hit math, you can hit convert to fraction, and so if you have a division, it'll convert it to fraction. If you go over to number and scroll down, you can also hit this numerator and denominator thing, and you can get 2/3 that way. Okay. All right. What we want to do, though, is be a little bit careful with the x. I don't want to just say add 2/3 and 1/6. That's not really what we have here. So I think maybe the easiest way to solve this using your calculator, again, is just to go back to graphing. Okay, so I'll pick that left-hand side to be my y1. Let's clear out the old stuff. So 2/3 x. You could write 2 divided by 3, or if you want to be fancy, you can make the fractions in here, right? 2 divided by 3 times x plus, go back to the math menu to get my fraction, 1 divided by 6. But if you just use division, it's all right too. Gives you the same answer. Okay. And here I'm going to put in my 1/4. Okay, so we hit graph. There's one line. I can't see the other line, but it's not because I haven't zoomed out enough. I'm zoomed out so much that I can't see the distinction between the line and the x-axis, because it's just 1/4. I'm going to go ahead and reset my zoom window. And then hopefully I'll be able to see it. And then I can see, okay, I went across. It's just really close to the axis. Okay. So now I'll calculate my intersection point. First curve, second curve, guess. And it gives me x equals 0.125. And maybe if this problem started with fractions, I would say, oh, maybe I want an answer in fractions. Okay, so that's where I could say, all right, take 0.125 math and convert to fraction. And it says, okay, that's 1/8. So we can get this nice fraction answer, even though we used a graph to get there. Okay, I think this is our last example. Yeah. The percentage of college freshmen whose average grade in high school was an A was about 19% in 1970 and has been growing at about 0.8% per year since then. Make an input table with at least 4 entries. So let's let x equal the number of years since 1970. Okay, and we'll say that y is that percentage. Okay. So if I just make an input-output table, when x is 0, so that's in the year 1970, it should be 19%. And then every year, that's going to decrease by 0.8. So what I can do is I can say, okay, start with 19%. And say, okay, I want to decrease that by 0.8. And then again, and then again. So if I decrease by 0.8, I'll get 18.2. Okay. And then if I decrease again, I get 17.4 and then 16.6. Okay. Now let's write an equation. Okay. And here they say, oh, they're going to mess things up on us. They're going to tell us our variables. T is going to be the years since 1970, and P is going to be the percentage. Okay. So if we had read further, we could have started by saying, all right, let's use these variables. So we're gonna pick T now, and we're gonna pick P instead of Y. Okay. And what I want to do is, if I think about a linear equation, right, I have this constant rate that we're decreasing by. Okay. If you remember, y equals mx plus b, b is going to be the value when x is 0. And m is going to be the constant amount of increase or decrease. So because it's decreasing by 0.8, I want the m to be a negative 0.8. But we don't want y and x. We want our y is equal to p and our x is equal to t. So we're going to have p equals negative 0.8 t plus 19. Okay. If I want to write that in function notation, I want to say that p is my function and my variable is t. So I would write p of t equals negative 0.8 t plus 19. Okay. Now let's compute p of 30. So what we did is we replaced t with a 30 on the left. So we replaced t with 30 on the right. Okay, so I'm just going to use my calculator to evaluate that expression. So I have negative 0.8 times 30 plus 19. Oh, I misread this. This has been growing at 0.8% per year. And I made it decreasing at 0.8% per year. So let's back up some of these numbers. So I want to add 0.8%. So after 1 year, it'll be 19.8. Add another 0.8, so it'll be 20.6. Add another 0.8, so 21.4. Okay. And since this is increasing, I want it to be positive. Okay. Sorry about that. So we want to take 0.8 times 30 plus 19. Okay, so we get 43. Okay, so P of 30 equals 43. Here's the tough part. Explain in context what this means. So I want to translate this back into words. Okay, so when T is 30, that's 30 years since 1970. So T equals 30 is the year 1970 plus 30, or 2000. Okay, so what this is saying is that in the year 2000, okay, my percentage is 43. Okay, so 43% of college freshmen had an A average in high school. Okay. Predict the percentage for 2013. So 2013 minus 1970 is 43. So what I want to do is I have T equal to 43. Okay. So I'm just going to plug in T is equal to 43. And again, I'm going to use my calculator to compute. So 0.8 times 43 plus 19 is 53.4. So we have 53.4%. Predict when the percentage will be 50.2%. So what I want to do is solve P equals 0.8 T plus 19. It's saying when, so I want to solve for T when P is equal to 50.2. So what I have is 50.2 equals 0.8 T plus 19, and I'm solving for T. Okay. So we can subtract 19 on both sides. So we have 50.2 minus 19. Right, that gives me 31.2. And now we're going to divide both sides by 0.8 to get t by itself. So I did that on my calculator, and I get 39. So t equals 39. So what I want to do then is say, well, it says predict when, so I want to convert that to a year. So t equals 39 is the year. Remember, it's 1970 plus whatever t is. So that's 2009. Okay. All right, what is the p-intercept? The p-intercept is going to be the percentage when x is 0, okay, or in this case when t is 0. So t equals 0 is the year 1970. So the p-intercept is the percentage in the year 1970. Okay. What is the slope? That one's a little bit more challenging. If I write down the formula for slope, okay, I wrote it with x's and y's, y2 minus y1 over x2 minus x1. I can think of it as the change in y over change in x. Or you could think of it as the amount of change in y when x goes up by 1. Okay, so back here we said the slope was 0.8, right? We wrote down 0.8. Okay, so what that's telling me is that the percentage is going up by 0.8% every one additional year. Okay, that's what the slope means. All right, that's it for this section.